All right. Let me get some stuff situated, and then I will start. It says my connection is unstable. Maybe I'm playing too many things at the same time. Okay, let me see if that's better. Whew. Let me get this out. Alright, let's get studying. Right now, it is going to be the extension of Boolean algebra. So, fun stuff. And I'm on the summary from this last lecture I watched. So, it's cool. Everything is good. Maybe I should finish my probiotic first.
We can use these to simplify things. The only thing we have to keep in mind is that we are working on a very limited set, so some things will be different. In particular, the OR gate, meaning the addition, producing slightly peculiar results for adding one. But if we keep that in mind, we have a very powerful way of simplifying something.
So, I'm on the summary, and I'm learning about Boolean algebra, and basically the different types of group theory, and then it compares linear algebra and Boolean algebra so that we can see the difference of the two and how similar it is. So different basic group theories are closure, associativity, existence of identity, existence of inverse elements, commutativity, and distributivity between two operations. So in closure, it's basically just two elements from a set, and basically the operation it has, the result has to be within the set of numbers. So for example, in linear algebra, we have a set of negative infinity to infinity, so 1 plus 1 equals 2. It's within the set, so it's a valid operation and a valid result. And for Boolean algebra, the set is 0 and 1 because Booleans only go from 0, which is false, and 1 which is true. So 0 plus 0 is 0, 0 plus 1 is equals to 1, 1 plus 0 equals to 1, and then 1 plus 1 usually in linear algebra would equal to 2, but since in Boolean algebra we only have zeros and ones, we either force it to be within the set, or it's either we force it to be within the set, which is we can contribute the 1 plus 1 to be the plus symbol to be the or statement, and then a 1 times 1 would be an and statement. And if we're doing addition, it could either be, which is one of XOR means one or the other has to be 0 and one has to be 1, and it's an exclusive one, so it can only be a 1 by itself. I hope that made sense, because it made sense to me. And then the associativity is when 3 elements are involved in an operation and the order of elements doesn't matter. Basically in linear algebra, 1 plus 1 plus 2, you can either group the 1 plus 1 and then add the 2 later, or group the 1 plus 2 together and add the other one later. Either way, it'll equal to 4. And same thing with multiplication. You can group the 1 times 1 or the 2 times 1, it'll still equal 2. So in Boolean algebra, we can create a truth table for 3 input AND gates. So AND means it has to be both false or both of them have to be true in order for the whole output to be true. So let's just say you have a 0 for A and a 0 for B, that will be false. And a 0 for A but a 1 for B, it'll still be false because both of them have to be true. And then, so we can apply that to a 3 input AND gate. And basically, if one of them is true or both of them are true, but one of the 3 is false, it'll still be false until all of them are true. So associativity, basically you can group different operations with each other, and so the order of the elements doesn't matter. And then the identity element does not change the original element when the operation is performed, which so basically within the operation, plus is in regards to the or XOR gate, and then the multiplication operation is with respect to AND, which is similar to linear algebra, 1 plus 1, 1 times 1. Inverse. Element produces an identity element when the operation is performed. 1 plus 1, 1. Cool. And then commutativity, distributivity, and then now I'm just focusing on the summary of the whole thing, which I should probably write down. Boolean algebra allows us to describe logic circuits using mathematical symbols. Yes. P. Do I still have an unstable connection? Let me check on my end. I think it's okay. Okay, I think it's okay. How do I add? How to add link on Insta? Oh, I didn't know you can put it. Hide the sad. Is this the same Boolean algebra?
Boolean algebra is very similar to linear algebra. It gives us rules at hand that allow us to simplify
Oh, it's the third one.
logic expressions.
Oh, I thought it was done.
However, since we are working with very limited sets in Boolean algebra, there are additional rules which come in handy to simplify and to change logic equations. So let's look at some of those. One of the rules that I would like to look at is the OR with 1. Another one is the AND with 0. And there's idempotency that deals with circuits that have identical inputs. And eventually we'll look at the Morgan's rules, which allow us to switch from one type of gate to a different type. So what about the OR with 1? The rule postulates that no matter what the other input is, as soon as one input to the OR gate is 1, the output will always stay at 1. How can we verify that? Well, we have to look at our truth table again.
We can use the truth table for the OR logic gate to prove the following identity. Use truth table. 0, then 1, then 1.
What happens if our second input B is always 1? Then we can look at the respective lines of the truth table, item, and we'll see that no matter what the input A is, the output will always be 1. So output then is going to be the second. That has important consequences. Consequences for circle. So if we, for example, have some products, our output will be that of organ. So if that is set to 1, no matter what the inputs are, it doesn't necessarily have to be the organ that is to go. It could be one of the inputs to go. So we have to check the input as well.
And this is important when debugging circuits.
The n is 0 can be verified the same way that we did the 1. We have to look now at the lines of the truth table where the input is 0. And we'll see that the output is
Hello. Stop being creepy. Is this a request? Oh my god. I can hear myself through your mic. I knew it. I was like, oh, there's two people in here. And then you joined, and I was like, shoot. Okay, I'm gonna go study now because you just ruined my groove, you know? Okay, bye. I love you. You better say back. Ah, you're rude. I know you're watching this, Donnie. My friend Donnie is rude.
Always. So the output of that AND gate that receives zero is always stuck at zero. But that has, again, consequences when you think about circuits. But we will also see later that this comes in handy for digital switching. What about that idempotency? The idempotency tells us what to expect.
Wow. Output will match input.
Tells us what to expect if we connect both inputs of an OR gate to both inputs of an AND gate in parallel. So what happens if both inputs are identical? Well, the rules say that the output will exactly match the input. Again, look at the lines in the truth table where both A and B are identical, and that's our top and bottom line. So the output in the first line will exactly match the inputs. And we can see that right here, where we have input A and output Y. If the input A is 0, the output will follow. If the input is 1, the output will follow. So what that means is we don't need the gate. The gate becomes redundant. What happens in case of the AND gate? Well, if our A is 0, our output is 0. If our A is 1, our output is 1 as well. AND gate becomes redundant as well. So idempotency tells us if both inputs of either AND or OR gate are connected in parallel, we can just eliminate the gate. It doesn't do it. Very interesting set of
Can eliminate it. De Morgan's rules. Rules. Type of logic gate with another except for inversions. For inversions.
rules has been published by Morgan. So the Morgan was contemporary of George Boole, 19th century, and he also looked at limited sets. What his rules postulated was that you can replace one type of logic gate with a different type of logic gate, except for inversions. So that's kind of a bold statement that we would be able to switch between AND gates and OR gates. So let's look at what the Morgan's rules state. So the first one says that product of two inverted variables equals the sum, the inverted sum. The second rule states that the sum of the inverted variables is identical to the inverted product of the variables. How do we verify that? Well, truth table is the way to go. It's kind of a complicated truth table, but it is just like that because we have to look at all the possible combinations. So we start off with A and B, then we have A naught, B naught. That allows us to form the product of non-inverted variables, the sum of three non-inverted variables, and the product of the sum of the inverted variables.
That was a long freaking truth table. A, B, A naught, B naught, A times B, A naught, or A plus B, and then A naught plus B naught. A naught plus B naught, A naught times B naught, A plus B, A plus times A times B naught, A naught times B naught, A plus B, and then naught, A plus. Confused. B, A plus B, A times. Oh, okay. A plus A naught plus B naught. So if A 0 times 0, 0, hold on, A naught is 1 times B naught is 1 equals 1. A naught is 1 and B naught is 0, 0, 0. A plus B is 0, so it's 1, 1, 0, 1, 0. A naught plus B naught, 1, 1, 1, 0. A times B naught is 1, B naught is 0.
So if we look at the first, the more Morgan's rule, we have to look at the product of the inverted variables, which is in this column. And we have to look at the sum, which is here, but we have to invert the sum. So that is here. And if we compare the two columns of this two table, we see that both columns are identical, so eventually we prove, of course, of the Morgan. The second one has us comparing the sum of the inverted variables, which is here, with the inverted product. Product is here, the inverted product is here. So if we compare those two columns, we say they are identical as well. So we've just proved the sum. So what consequence have the Morgan rules? They allow us to replace the OR operation with an AND operation and vice versa. That leads us into gate equivalency. So we've just shown that AND gates and OR gates, except for convergence, are equivalent. In our first example, we can use an OR gate with inverters at the inputs, and just to state
OR gate with inverted inputs.
space, we could just remove the triangles. So the OR gate with inverted inputs is functionally equivalent to an AND gate. An AND gate with an inverted output. So that's where our
Okay. So inverted OR gate, an OR gate with inverted inputs is equivalent to an AND gate.
combination gates and OR. So the same thing applies to the second OR rule, where we can take an AND gate with inverted inputs. Again, we can drop the inverter, we can drop the triangles, but we need the inverter models there. And we can replace that with an OR. So that allows us to switch between different types of logic. Now, combining the rules that we learned about previously, and in particular the idempotency rule, we can go even one step further. So what happens if we
Algebra rules. Give place
could take an NAND gate and wire both inputs in parallel. Well, idempotency tells us that the AND gate doesn't do anything anymore, but since a NAND gate is an AND gate that has an inverter, a NOT gate following the AND gate, we still have that inversion in place. So eventually, we will realize a NOT gate by connecting two inputs of a NAND gate in parallel. So we realize the NOT gate. How can we build an AND gate just using NAND gates? Well, we can use an AND gate by using a NAND with a subsequent inversion. And rather than putting NOT gate there, you can just use what we verified, use a NAND gate with inputs connected in parallel to invert the output of the NAND gate again, given as NAND. So the only thing missing is the OR gate. Looking back at the Mormon's rules, we can realize an OR gate just by inverting the inputs of a NAND gate, because a NAND gate is identical to an OR gate with inverted inputs. If we undo the inversions by putting the NAND gates with connected inputs, we get these inversions. So say that.
Whoa. Professor, slow down.
The NAND gate is functionally complete. So to summarize, OR with 1 and AND with 0 are important rules to keep in mind when debugging circuits. The idempotency helps us to eliminate gates, just drop OR and AND gates, and And the Morgan's rules allow us to switch between OR gates, AND gates, and vice versa. So eventually, we can replace all the gates in a logic circuit with one type of gate. For example, NAND or NOR. And that is very important if you want to build integrated circuits just using one particular type of logic.
Alright. 3 more lectures to go for my digital design class, but I'm gonna move on to math because I'm getting burnt out. Two sheet hyperboloids. Okay.
Just saying. Because it's not really totally apparent what's going on. So, all right, what do we have? Right there, what do you have? Or not right there, at least think it through. What do you have? Do you have all squares? Do you have constant? Does it look anything like what we want to write? Let's start solving that. What would you do here? Okay, move the what first? Probably the constant, yeah. And then I would reorder my variables. Ooh, but what's it gonna be? Told you, it's not super necessary, but standard for variables. What number do I want right there? Because I don't know a positive number, but notice what's gonna happen. Notice, if you try to tell me what's going on right now, you are going to tell me a one-sheet hyperboloid if you do not take that into account. Does that make sense? Get it centered for me and make that mistake. So let's divide by the -9, and we're going to change all of our signs. Now it starts looking like the standard form for something. Now we write stuff down. So now it's all squares. Now it's 1 plus. Now it has a constant. That right there says 1 negative, 1 sheep. 2 negatives, 2 sheep with a constant. That's how I always start. Now let's talk about a couple other things. What axis is this 2-sheet hyperboloid? You don't know even what they look like. We're kind of inventing this as we go. What axis should this be traveling along? The X and Y and Z.
Y-axis.
So listen, it's got 1 plus. Yep, 1 plus. All power 2, we got it. Has a constant? Yes. We're traveling along the plus axis. We're traveling along the y-axis. In this case, we'll be with that. Now we're only going to get 2 real traces out of this because our first trace gives us intercepts. Where we treat it like a circle with or an ellipse with 0 real dimension. It's an intercept though, and that's what's going to give us. How to find that? How to find that? Set both of your negative variables, set them both equal to 0. Set them both equal to 0. And what that does, it has to give you something on the intercept of the y-axis. It has to be something on the alternate axis. If you set both the other variables to 0, you're on axis. What variable should we set equal to 0 first? Hey, if you set x and z equal to 0, you get y squared over 9 equals 1. Super hard? Not really. What's y going to be? That's it. Just don't forget plus or minus, because we have 2 sheets, 2 sheet hyperbole that go in opposite directions. So here's what I know. I'm going to draw first piece here. I know that because I'm limiting my z to 0 and my x to 0, I have to get on the y. Wherever on the y, wherever positive here. At positive negative 3. At positive negative 3. Sorry, I'm writing small, but this graph's going to get a lot bigger here real quick. Now, the other ones for the traces. It's still going to be plus or minus, but I want to plug in a number that when I square it is going to be divisible by 9. That's what I want. Why?
3.
Because I want this to be a nice number. I don't want fractions. I want to be able to subtract it and then change my signs. That's what I want. What number should I use? If I plug in 3, I'm going to get 0. Why? Because we literally were solving that value. You can see what I'm talking about? They can't pick these numbers. Those intercepts are going to be 0. That's the only problem. So when you pick, you'd be smart. There's another way for me to tell you to think about it. I would pick something like 6. I'd pick something with a 3 in it. Because when you square it, 9, when you square it, we get a 9 squared, we get by 9. That would be 6. That's the smallest number that we can square that's divisible by 9. So we'll do that. Did that logic make sense to you? I know that it's kind of weird, right? Because you have to really think about it. But pick 6, that way you're finding something that when you square it, you can divide by the denominator. So when you pick that, hey, plug it in. Whether you pick positive or negative, you're still getting 36. This is going to happen every time. Every time. You're going to get negatives everywhere. What do you do when you get negatives everywhere? Change all your signs. And then one last thing. I don't like that number. How would you get rid of that number? Am I losing you guys? I don't want to lose you. How do you do that number?
Divided by
Divide
3.
everything by 3 is multiplying the numbers by 3. I didn't promise it was going to be nice. I just promised you we didn't know how to do it. Let's see. What shape is that? Come on, what shape is this? That's right. Parallel to the XZ plane, but not on the XZ plane. If you can answer this, I'm going to be happy. Happy. I'm not going to get it wrong because I'm going to get mad. You're a monster. Okay, don't do that. Where is this ellipse that has a rate of x goes along square root of 7, while z goes along square root of 3? Where does that occur? At y equals what value?
Y equals
So whenever you plug in, go to that value, redraw the other two axes.
Oh my god.
You didn't know I was home?
No. I was watching my lecture. Stop! Stop!
Oh, you're changing up. What's on YouTube?
Oh man.
Who's in right now?
It's Donnie. I don't know if Matt's still here, or then another person. Go. Stop. You're crazy. Yes, I know.
I know it's time intensive. I really do apologize for that, but if you're gonna do it right, it takes some time.
I'm debating if I should go to the gym
It's
or
a
not,
great thing,
because I still haven't finished this lecture.
Go to finish your lecture. Go to the gym tomorrow.
Yeah. Well, there's no more people.
Huh?
It's because you took off your. It's
Yeah.
because you took off your belt. I'm just kidding.
Something was wrong with my ankle at work.
Really? Okay. Make sure you rest, because that's important. Oven closed. Oh my.
So, hey, can someone tell me this x? What's the square root of 27 about? No, that's exactly 3 root 3. I mean, I got it, so I can actually do it on here. Come on. How much?
Oh, I don't even have my calculator
Square
on.
root of 27 equals 9, about 9, 9.5, 5. Okay, so about 5. Let's go to about 5, a little past 5. I sure want to talk, I don't want to have to repeat all this stuff, but check it out. 8. Set both these equal to 0, you get your line yourselves. Put it right there.
You don't want
Pretty
to
good
close the
number. And then
door.
the next, the denominator divides by square. Subtract it, change your signs, divide it. You now have a
Who is watching now?
It's taking
I don't know.
place.
Hello.
And y equals negative
How?
6. And y equals 6. It's going to be
No, you
ellipse.
can't.
It's going to be ellipse. The x spreads out about 5.1 plus or minus. Square root of 27, about 5.1. Does that make sense? The z, how much is the z spread out? About
Right? You can't.
1.7 square root.
Mm. Hello.
No, it's time intensive. I really do apologize.
Sorry.
If you're gonna do it right, it takes some time. It's a pretty creative graph though. Hey, can someone tell me this x? What's the square root of 27 about? No, it's exactly 3 root 3. I mean, I got it, so I can actually do it on here. Come on. How much? root 27 equals 9, about 9, 9.5, 5. Okay, so about 5. Let's go to about 5, a little past 5. Are you seeing what I'm talking? I don't want to have to repeat all this stuff, but check it out. 8. Set both these equal to 0, you get your line intercepts. Put it right there. Find a good number, a number that the denominator divides with a square. Subtract it, change your signs, divide it. We now have an ellipse that's taking place at y equals -6 and at y equals 6. It's going to be an ellipse. It's going to be an ellipse. Where x spreads out about 5.1 plus or minus square root 27, about 5.1. Does that make sense? The z, how much does the z spread out? About 1.7 square root. So on my like z axes that I shifted over, we're about right there. We're just sketching, but that an idea is really nice. What it looks like. On the x,
Oh, snap.
Yeah, I think let's skip today. My knees are killing me.
Okay.
square root 3, up and down. Square root 27 is about 5.1, 5.1.
You want to go to the terrace and study?
It's raining.
Still want to go?
It's raining.
You see how
Yeah,
redrawing
and?
the x-axis and redrawing the z-axis, that's what you make it.
I'm gonna eat though, real quick, because I'm hungry.
Okay, I already ate. Not dinner. Okay, I had some for lunch, so we're good. We're in the clear. So redraw. So 5 is over there. One, two, three.
Your life's a lot easier. Trust me on that. That's what you get. Right? Otherwise, you're like, I don't know. It's really hard to tell. You get some really crappy graphs. They're all really crappy. If you're not ready this by hand, but don't make it worse by not doing that. So from here, here's the cool part about it, though. The cool part about it, if I can draw this ellipse, which I know is taking place at x equals 6, it's going to be hard because it's pretty extended here. And this one,
Oh, shoot. Shoot.
and here's what happens. We connect this. Basically connect dots.
What the heck?
Sorry, it's not better. Can you see the picture I'm trying to present to you?
I'll be right back. You're welcome. What the heck did I just draw?
Picture is this one. The picture is these bowl shape, almost parabolas that are coming out this way and coming out that way. There's nothing between them. That's called two sheets. If you were to wrap these presents, you would need two sheets of wrapping paper to cover those things. That's why we call two sheets. So we need one sheet. We have one shape. Do you guys get the picture? Yes, no. Yeah, I think so. Are you sure? Could you do it? Do you have any questions about it? Could you at least tell the type of shape it is by looking at the formula? Oh yeah, okay, hey, constant, L squared, 1 plus 2 sheet method along the y-axis. Do you know why in the world I'm plugging in 6 and negative 6?
Yes. So that the 9 can be divisible by the
And then that's going to
numerator.
give us these nice ellipses at these values on the direction axis that we just plugged in. Or we'll show hands feel okay with that. Okay, we got a couple more. Couple 3, actually. So we're going to talk about cones. I think we're going to take a break after that, and then we'll come back and finish up paraboloids and hyperbolic paraboloids. Super fun. So let's talk about cones, and we'll call it good. Cones. Here's what cones do. Here's the difference between. Let's see if you're paying attention actually. Cones are easy, by the way. Cones are really nice. I'll show the easy way to do cones. If you know what that is, I'll be happy. What is it's not a cone. Okay, it's not a cone. I'll change it. What is that? Beautiful. I mean, one minus. All squared. Boom. So the difference. You see why you need to be familiar with these things to get them right. Because if you have the same exact jump, but you don't have that constant, that's not a cone. Here's what's nice about our cones, though. Our cones are always going to be crossing at the origin for us. We're not going to be shifting them around. So I know that these cones, and by the way, cones are a full cone. So up and down. So we're going to have cone and cone. That's what's going to go on here. Here's how to tell. They're still all power 2. Go back to they have 1 minus. The big deal is they have no constant. What's the odd 9 out? The pluses or the minus? What's the odd 9 out? It's going to travel along the one with the minus. Is me teaching this way making sense that you can see the differences between them, the odd 9 out sort of thing? These all, if you want to write another note that I might write up there, they all cross at the origin. Again, just look at this for a second. Don't let this yet. If I set that equal to 0, it's a total.
That is a circle.
Doesn't even the origin. Oh yeah, I have to have zeros here to make that happen. Doesn't even the origin. So because neither of them are negative, you can't subtract anything without positive. So this, if I set that equals 0, we're at the origin. That's why I said write down all of these plots at the origin, because you don't ever set this equal 0, because it just shows you that you're at the origin. So if you want this says nothing. Or it says you're at the origin. That's what that says. So the idea then is, let's plug in some values for the negative variable that again are divisible by the denominator. That's what we want to do. What this is going to give you, I'll plug in some numbers here to the negative variable. Please look for a second. If I plug in numbers here, it's going to give you a number. It's going to be a minus number, which I will add to the other side. If I add that to the other side, we have a constant up there, and that gives me circles or ellipses. Do you see it? So plug in some numbers to that variable, add it to the side, and then we have circles and ellipses. That's what you do. That's right. Tell you what, we're gonna break through one pretty quick. Yeah, we're gonna do just two, the parabolas and the hyperbolic parabolas. If you look at this and it says, can you tell me what that is? How can you tell? This first one we have not by a constant, but they're all squares. However, wait a minute. How many minus are you supposed to have? There's two. Did you just move all of these out or just change the signs when you have that zero? Just take care of that. So if you have this, oh man, I don't see a constant, so there's no constant. All square, that pretty much looks like a column to me, except for the fact that this has one minus, this has two. When that happens, you have zero, it's the same thing. Just change all your signs, divide by the whole time, and leave the other side out. Here we go. Let's put in the correct order. Here we go. Okay, let's add this. Let's add this. Let's subtract this. And I'll add it. Two negatives are different. So like that, you want to can't because it's zero, right? So I mean, it is the same thing as the it's just we have that format to make it nice for us because all this stuff we will show you that. Does that make sense? You guys okay with that one? Are you sure? You're sure? I'm fine with it. No, it doesn't quite look like that. Could you make it look like that? The standard form's pretty nice, right? What would you do? Yeah, zero, right? You can divide that by anything you want except zero. What would you choose to divide by? I divide by 36. Let's do that. If we divide by 36, that at least looks a little bit better. It's kind of nice. So now we go, okay, yeah, that looks good. There's no concept of all squares with one minus. That's for sure. Okay, where are all points centered at? So for us, yes, sorry, we're not going to be shipping them. If they're all centered at origin, that acts like one trace. I love that. What axis is this going quickly? What axis is this going directly on? Why? How do you know it's going on the axis? The origin acts like a trace, like one trace. It tells us this. That no matter what, I'm crossing there. That's what we're doing. I'm crossing there. The other two traces, that's what this stuff is for. It's putting some values for the negative variable that are divisible by the variable. Now, here's the nice part about this. You can always use that if you have put it in standard form. Cool. So what number will we use to plug into the what variable? What variable, what number?
Who's talking? It's Professor Leonard. Really good professor on YouTube University. Really good for Calc 3. Saved my life multiple times.
What number would you use? 6. Plus or minus. One trace at the origin, or the other trace. Let's do that. If we plug in plus or minus 6, we're going to square it. It's going to be 36. Oh, I love that. Also, if you do that, this is beautiful because when you add that to both sides, if you pick the correct number, you get 1. And it's already in the form of circles and ellipses. Boom! I love that stuff. Now we take the time to really make it look nice, and it pays off good. It's like you're not going to want to brush your teeth, you know? You don't have to, but When you're in the math lab and I start talking to you and you're not like, okay, wow, a little gamey. There's two, dude. This is supposed to be your math and hygiene so that you're doing good later. So it makes it easy. Right? So at this x equals plus or minus 6, here's what we do. It's pretty easy. Let's go, hey, what value did I just plug in? What axis did I plug it in? Z, 6. That's Z. And I just plugged in 6. Now at 6, plus or minus, what shapes am I getting? Ellipses. Ellipses with the x spread out plus or minus 2 and the y spread out plus or minus 3. What that means is just like before, wherever you just plug in the values, go to this axis, go to this number, and right here, redraw the other two axes. This is the first time we're doing the z, it works really well with the z, always good. So at those values you just plugged in, so z was negative 6. Redraw into the y. Gotta be careful. Redraw into the x. Y.
I can see you.
And then all those images of the axis that we just shifted up, it's all we're doing, we're just shifting this up and then we get the picture. Where are we shifting it? Plus or minus 6 on the z-axis. Where those new images are,
I don't know. Say hi.
This shape on this shifted up image of your x, y.
Say hi.
That's what traces do.
Go study too.
You want me to join your live stream?
Sure.
I have 4,000 followers, you know.
My bad. So sorry.
So with 2 x, or the image of the x, 3 on the y, or the image of the y, we draw our ellipses.
So 2 for x. -2. Oh, this is Yue. She's our study buddy. I have 2 more. And then 9. Are you just playing with them in the back?
Now here's what's, I'm going to do it logically, I'm not going to prove it, I'm going to do it logically. What's happening is we start off, and I remember we would get some ellipses. Do you understand? So these ellipses are just getting bigger, 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 bigger. They start off at 0. That's our first trace. It's a technically ellipse with 0 dimension. So what this is going to do is we're going to create this or that crosses through the origin.
Cool.
Good job. Was that good? Makes it work pretty fit. It sounds like I know what I'm doing sometimes, you know, almost. Just pretty use this technique, it actually works. That's an image of the film that we just created. Do you guys see the plan that we're creating? That's the plan, man. We've covered 4. We got a couple other ones. Honestly, the next one is the easiest one we've done. The parameters. I think we need a breakout, so we're gonna do that. We'll come back.
Oh, I thought it.
All right, so welcome back. We got our 2 more.
I thought it ripped. Please. You know what's funny? I've only been in Calc 3 for like a week, but then I have this many notes already. It's a thick pile. Almost done with this lecture, and then I'm going to move on to more about cylindrical, spherical uses, and then I'm going to move on to vector functions and space curves, then arc length, and motion in space, velocity and acceleration, which I guess ties in with the vector functions and arc length and everything. And then after I finish all my lectures, I might end up doing my homework, my last homework piece, or I might go back to my digital design class and finish the lectures there. So all I have to do this week is purely homework and lab. Okay. We got
More
this.
shapes, the ones that you probably try doing homework, like what's those ones without squares? The last 2. That's those ones without squares. We get 2 more shapes. Paraboloids, hyperbolic paraboloids. And you go, all right. What we've been kind of rolling with is, here's the formula, here's how to tell what shape you have, here's some major notes on it, and then I'm going to give you one again. We're going to keep on going.
Also, hi everyone. How are you doing today?
And see how it differs from practically all the other ones that we have had.
Are we all studying hard or just watching people study?
Man, you're gonna notice something right off the bat. If you look at some of those formulas, like on your program you've seen before, they look completely clear, like automatically. So if you have, okay, let's recap a little bit. If you have 2 variables, I don't even care what you get 2 variables. What do you have? So you got. So what do you got? You have 2 variables. Yeah, right. What do you have? You have 2 variables. Yes, so along the axis that the variables.
Also this.
We got 3 variables, we for sure have surface. So it's going to be a surface, it is a paraboloid, but it looks different from what we had before. Everything else we've had is that everything being square. This is the first one we had that doesn't have that. So if we have 3 variables, and one of them is not squared, we have one of the last 2 shapes. We have a paraboloid or a hyperbolic paraboloid, which we'll talk about in just a second. So paraboloids look like this. How to tell what they are? 3 variables with 2 squares, that's the first one.
3 variables.
3 variables with 2 squares. Also, the variables with the squares have to be positive. They gotta have pluses in front.
Oops.
That's pretty much it. The third thing I wrote down probably goes, probably more on notes. So the notes I want you to know about this is really the number one thing I want you to do is be able to recognize these shapes. That's a pretty big deal. Have it in your head what's going to happen. One way to do it is by recognizing, hey, all squares, all pluses, the constant we have, and we're one of these shapes. With paraboloids, it's important to know there's only 2 squares. There's 3 variables, only 2 squares. Also, what I want you to see here is that that constant, whatever, if there is one, whatever that is going to give you the direction that that parabola opens in. So if we have a plus, it's going to open towards the positive of this axis. So a few notes here. Parabolas travel on the axis of a variable of degree 1. So it's always the degree 1, that's the axis that this thing opens along. Is that making sense to you? Are you guys focused in today?
Wait, you went through that very quickly.
With paraboloid or hyperbolic parabola that you talked about just a second. So parabolas look like this. How to tell what they are? 3 variables with 2 squares, that's the first one.
Also, I will be right back. I gotta study now. I'm back. Do you want to be part of it? Do you want to be part of it? You're so too much. I'm back. Yes. You're distracting me.
Sorry.
Come study with me. Oh my gosh. You can stand there forever.
3 variables with 2 squares. Also, the variables with the squares have to be positive. They gotta have this in front. That's pretty much it. The third thing I'm going to write down probably goes, probably goes more about notes. So the notes I want you to know about this is
What you mean?
the number one thing that I want you to do is be able to recognize these shapes. That's a pretty big deal. Have it in your head what's going to happen. One way that we do it is by recognizing, hey, all squares, all pluses with the constant we have, and or one of these shapes. With parabolas, it's important to know there's only 2 squares. There's 3 variables, only 2 squares. Also, what I want you to see here is that constant, whatever, if there is one, whatever that is going to give you the direction that that parabola opens in. So if we have a plus, it's going to open towards the positive of this axis. So a few notes here. Paraboloids travel on the axis of the variable of degree 1. So it's always the degree 1 variable. That's the axis that this thing opens along. Is that making sense to you? Are you guys focused in today? Okay. So the paraboloid opens along the axis of the variable of degree 1.
Opens. Long axis. Okay.
Little side note. The coefficient of that degree 1 variable is going to tell you how that paraboloid opens, whether it's opening towards the positive axis or the negative axis.
So it determines where it opens.
I should say it this way, the coefficient of the degree 1 variable gives you direction. A positive coefficient means it's going to open along the positive axis of wherever that variable is.
So if it's positive, opens.
And negative means it opens, you can think up and
Towards.
down, but unless we're talking about the z, up and down doesn't work that well. So I want to talk about opens towards the positive part of the axis or the negative part of the axis. So the negative opens, this paraboloid will open towards the negative part of the axis. And then the last little note. The idea behind this, and hopefully you see it, what's going to be really nice if we have this in this form, we don't have to get it in this form, but what we really want to have happen, we want to be able to plug in 0 here, and if we have a shift, if we do that, if we plug in 0 or a number for the 1 degree variable, if we do that, what we're going to get is some sort of a trace on a plane parallel to the two of the variables. Set the degree 1 variable equal to 0 to get a trace on the forward plane. I'm going to make a little side note. This works only if the paraboloid is shifted. If it's not shifted, then you start plugging in other numbers for that 1 degree variable to get traces on parallel planes with the forward plane. A little bit above and below, we talked about things like that before, but I want to show you an example. So let's start with this one. Number one thing, you notice something really funky about this one compared to everything else that we had before. What's the first thing that stands out to you here? Number one, how many variables do you got? Okay, but what? One of them's not square. Right there, that's none of our previous shapes. So this is a new shape. We were talking about write down everything? Write down everything. So we got 2 squares, we got 3 variables. Also, we notice one more thing. Are both squares positive? So what we're looking for is we want 3 variables, but we want 2 squares, and we want the variable, the squares, they're positive. That's what we have. So right now, this tells us that we have paraboloid. Let me ask you a question. What axis will this paraboloid be opening along? How can you tell? Now, how about this one? Will this be opening towards the positive z or the negative z? What do you think?
Positive z.
What's the coefficient right in front of it? Or positive z values, or positive z axis. Are you opening upward if you want to? I don't really care. As long as we get that picture down in our head. Now we're going to do one more thing here. We're going to check this out. It's that deep. It's a shift. If you know anything about graphing functions at all, whenever you have it looks like a function, right? This is like an f of xy. It is a function. We have couple of functions with a will. But yeah, a single variable equal to something else and all the other variables, that's a graph. And when we have at the very end, something minus or plus, that's always a vertical shift or a shift along the axes, where plus means towards positive or minus means towards negative. So I'll tell you right now, that's a shift down of 4 spots. So here's our z-axis going this way. Whatever's going to happen, this thing is going to be shifted down 2, 3, 4 spots. Show you guys can understand that. Okay, so that's some basic graphing, but that's important. I want to show you another format that you're going to see it, because right now, if you look at it, this isn't anywhere close to that form, right? And we don't have to put it in exactly that form, but getting close helps. I'm going to show you this. What I'm going to do right now is I'm going to add that 4 over. I'm going to add that 4 over. This is typically how I like to put the formula or the equation for parabolas. There's only one drop here. Please listen. Please listen. A lot of people get really confused. Wait a minute.
Oh.
Wait. That's now a shift up 4. Listen, I can't alter the shift just because I put it in. Get your shift right. All right. I can't alter the shift just because I put it in different format. I want you to think about it this way. Anytime I ever have a number being added or subtracted right next to a variable, it's a shift, but it's like opposite of what your brain wants to think. So when I have that z plus 4, it is a shift along the z, but it's down 4. It's not up 4. Only when you have one variable solved for that variable do those numbers at the very end go the direction you want them to go.
Mm-hmm.
Any other time it's pretty much backwards. So it makes me okay with that one. So this right here, that's a shift of 4 towards the negative axis is how I'm going to say that. You can say down 4, I don't care, but this is shifted. Let's say down 4.
Oops.
That's a shift down 4 on the z-axis. Let me test you here real quick. Just a little aside, okay? What if this piece of it, would be negative z minus 2? Would that paraboloid, it still be along the z-axis? Recognize that. Okay? Would this be opening towards the positive z, or would this be opening towards the negative z? What do you think? It would be opening towards the negative z. That's what it'd be opening this way, for sure. Why? Because that's negative. Even if you distribute it, it's negative. Now here's the next one. Is that a shift up? Or down? Yeah. That's what you want to do. You change your answer back. Down. There's a describing dance. I like to dance. I have to dance. You don't want to see that. We're searching on math nodes. It's up. It's opposite of what is next to that z. That's up. Wait a minute. Hold on. That's plus 2 though. That's plus, but that's negative. That's negative. It reverses things. So if you were to solve for, if you were to have this. Please watch. If you're confused on this, please stop whatever you're doing. Just watch for a second. If you have this, you got to change a whole bunch of signs around, right? You got to change stuff around. Firstly, it probably destroys our shape. But secondly, this becomes, if I solve for z, I subtract the 2, but I change the sign. That becomes a plus 2. At the very end of the function, it will be shifted up. It destroys our shape. I know that, but I'm talking only about the shifts right now. Because I'm talking about the shifts right now. Yes, no? I gotta pronounce that word real carefully. Shift. That right there would be a shift up 2 spots. When you have a number being added or subtracted next to your variable, it is opposite of what your brain wants to think of it.
Hello,
So
everybody.
Shift
By the
down,
way.
here shift up. That's the idea. Now I want to get back to our example. what I told you is that if you have that degree one variable set equal to 0 and you have a shift, it's cool. This is probably a nice shape. I'm no kidding. It's probably a nice shape to graph because it's going to give you one trace, and in this case, one trace is enough. Unlike the other ones, one trace is enough. So what are we going to set equal to 0? The x, the y, or the z? Set the 1 degree variable equal to 0.
Yes. Z equals to 0.
Do you see it? You see something really nice. Now, I hope that you notice this. Every little time you have this, you really try to put things in standard form. Please notice, we didn't do that here. This is one of those times where it's easier not to, because when you plug in 0, you get something you can divide really easily. That's kind of a nice thing. So when we don't have that shift, yeah, sometimes standard form progress. When we do have the shift, don't put it in standard form. It's part of with that +4 when you start dividing stuff away. Does that make sense? So plug in that 0, you go, okay, hey, now we can put standard form. Now we can have stuff like x squared and 4 plus y squared and 1 equals 1. Everyone in the class right now, what in the world is that and where is it located? What is that?
It's a
That's an ellipse. X gets spread out
ellipse.
Y gets spread
Plus
out
minus 2 plus and
So
minus
that on
1.
the x-axis plus 2 minus 2, on the y-axis plus 1 minus 1.
Mhm.
Where? Okay. If you get it, so happy. That's like a double whammy. Sneeze and a boo. Where is it?
It's at
What
negative
is
4.
z equals 0? What is that? What plane is it? Come on, what plane is that? That's just that's right. That's what I said. You're going to put it on the plane. It's really nice with these parabolas. So when we draw I had one yardstick short meter. Yep. Still my yardstick. Okay, so when we draw this, we notice something, right? Whenever we do these traces, we go wherever we plug the scan along, whatever axis we direct along, and we redraw the XY axis. We're doing that, except if we're at z equals 0, we literally already have that. Draw this ellipse at that place. That's what makes it nice. So we knew that we were going to go out x equals 2 and negative 2. Y equals 1 and negative 1. Let's draw our ellipse right there. But we also knew something else. We knew that this paraboloid was shifted down 4 on the z-axis. What that does, that gives you the z-intercept. So I know a couple things about it. I know that along the z-axis, I shifted down or towards the negative 4 spots. I also know something else. Check this out, it's pretty cool. Okay. What axis is this opening along? The z. So that makes sense for the z. Is it opening towards the positive z or the negative z? So I have to intersect here. I also have to open this way. I also have to have that trace, which means that this paraboloid is going to go from here, from here, from here. Oh man. We get that shape, sort of, if we can visualize that. I want to make sure that at least I've explained this well enough. Can you guys visualize the paraboloid? It's a parabola in 3D. That's all it's doing. It's just taking from this negative 4 on the z-axis, opening this nice little base, opening upwards. So you guys feel okay with that one? Any comments, questions about it? If I give you that on a test, would you be able to do it? Are you sure? So the idea is, hey, look at your equations, make sure you have three variables, only two squares. Both squares have to be positive. And then if you have a shift, just set that now. Identify the shift, know where you're at and where your axis. It's always
That's
traveling
easy.
along your axis with degree 1. Set that equal to 0 and you use some circles or ellipses. It's going to give you a trace on the fourth plane. Combine that with your shift, and you got this nice, pretty easy picture. You only need one trace here. Are you sure you're okay with it?
Yeah.
Okay. Now stop. Just real quick. What if that's not there? What if that's not there?
Then it's
Is that shift? Okay, wait. Is it still along the z-axis? Is it still open towards the positive z-axis? Yeah. It's going to be this, but it's going to be here. It's not shifted any longer.
Mhm.
So, but the problem is that eliminates that trace for us. So when you get something like this, you go, wait a minute. If I plug in 0, verify this. If I plug in 0 for that, there ain't no way that's happening. It literally cannot happen because you can't add a positive plus a positive and make 0. It's not happening. So when that happens, take some logical numbers that you would plug in, like I don't know, something that's the common denominator of these things, like 4. I plug in z equals 4. You guys see the point of doing that? You plug in z equals 4. Then when you divide by 4, actually the same thing, except for one thing. Please watch carefully now. I don't want to worry about it, okay? That looks exactly the same as what we just had, correct? Except it's now z equals 4. So what that would do is you come up here, you redraw your x, redraw your y, and you have your trace right there. It would basically undo the shift that we just talked about. I don't even know if that makes sense. We're getting a whole lot of kind of looks from you guys. Is this making sense to you?
Yes.
So if you have the shift, it's easy. Plug in 0, done. If you don't have a shift, plug in the common denominator of these things, and just when you divide, you at least get a reasonable trace and a reasonable value along the z-axis. The real show gets real here. Okay, we're going to talk about the last one. The last one says, you know what's going to happen, right? As soon as you start changing anything about that formula, our shape starts changing. So what I'm going to do, that. It's going to give us an entirely different shape. And what we call this shape is a hyperbolic parabola. Here's how you tell. It's got 3 variables. 2 of them are still squared, but one square has a minus or a negative.
X
The degree 1 variable still gives us the axis of direction, our directrix or direction axis, but it works a little funny. So degree 1 variable still gives us the direction of travel, our direction axis. This stuff's going to change, and the whole I can just do it. I'm going to say this is how you do it. But I want you to understand why. I want you to understand why these shapes are the way they are. So here's what we're going to do. We're going to plug in both positive numbers and negative numbers into the degree
Hi,
one
V.
variable. Plugging both positive and negative into the degree one variable.
How are you? What you up to? I get to breathe with you now. You do. You start your own live stream.
I want you to see that. I want you to see that.
And I can watch you and then breathe with you.
If I plug in a positive number here, so that this is positive. I say, hey, positive number. This is just a positive constant, which I can divide by. I can do that. What do we get? Those of you who watched comic sections and you know this, x squared minus y squared. What do you get? What is that shape on a plane? What is it?
I know. Can that happen with like Zoom, or does it have to be like exactly a streaming software? Because I don't know how to do that on YouTube at least.
Do this like that.
I can't see the board.
That's it. How do you know which one it is? This one along the x.
I'm surprised there's actually like 5 people in here though. Okay, will do. Love yous. My phone's right next to me, so if you need to message me, you can do it in the chat too. But my phone's right next to me. OnlyFans, I'm dead. No. It's supposed to be lonely fans.
X comes first and is positive. So if I put a positive number, I get hyperbolas along the x-axis. Does that make sense? But wait, if I plug in a negative number, and divide by negative, the signs change.
Yes.
The y is coming first. Is it still a hyperbola? Yes. But now it's along the y-axis. Isn't that interesting? So we get this shape, depending on whether we plug in positives or negatives, that the hyperbolas switch from doing this x hyperbola to doing a y hyperbola. But this is those things that you probably confuse with parabolas. They're not. They do this like that, or they do this like that. They do these sequence. That's it. How do you know which one it is? This one along the x-axis happens when the x comes first and is positive. So if I plug a positive number, I get hyperbolas along the x-axis. Does that make sense? But wait, if I plug in a negative number and divide by negative, these signs change. Now the y is coming first. Is it still a hyperbola? Yes. But now it's along the y-axis. Isn't that interesting? So we get this shape, depending on whether we plug in positives or negatives, that the hyperbolas switch from doing this x hyperbola to doing a y hyperbola. And we get this really unique shape of a hyperbolic parabola. So the whole idea, it's still going to travel along the axis of the degree one variable, no problem. Now you're going to figure out, plug in some positive numbers and negative numbers of the same value, typically, and then we're going to get 2 types of hyperbolas, some along the, in this case, x-axis, or in other case, y-axis. Let me show you an example that's going to really clear things up. Also, just like before, it's not super necessary to put these in standard form right away. It actually works a little bit better if you don't. There's only 2 examples that work that way. Other ones, man, standard form is so nice. But here it's kind of nice to deal with it without standard form. You just divide a number away, especially if you have such a shift. It works better. Okay, so your test is coming up, and I give you this problem on the test. My first question is to you: do you even know what it is? Can you identify what that true or false? It's a cylinder. That should be like immediate. How do you know when something's cylinder? Come on, put it all together. How do you know when something's a cylinder?
2 squares.
2. This says 3, not just
3.
2. So it's definitely a surface. What type of surface is it? Well, how many squares does it have? Okay, two, and so it's either what one of two shapes. It's got three variables, two squares. One of two shapes. What is it? Paraboloid or absolutely. Now, doesn't look quite good to me. I noticed that on both the paraboloids and hyperbolic paraboloids, I have my squares on one side and my 1 degree variable on the other side. So when we solve that, we're okay, hey, there's one of the two shapes, now we know what it is. Tell me everything you know about this. What do you see about it?
3 variables with 2 squares and 1
It's
square
got
that
two
has a
squares.
negative.
2 squares. 1 negative and 1. What is it? How do we know? Sorry, how do we know what shape is it? Is what I'm asking you. What shape is it? What differentiates a hyperbolic paraboloid from just a regular paraboloid? What separates that?
Negative.
Good, perfect. So if that was a plus, we have another paraboloid. Since that's a minus, we have one of these negative. We know that this is a hyperbolic paraboloid. Everyone in class right now along what axis? Come on. Boom. Along Z. Now, I can't tell you, or I can't ask you, how's it open? What is open? That's not what this is all about. You see, what's going to happen with all of these hyperbolic paraboloids is that all that's going to happen is that the positive values of Z and the negative value, you can see it. Plug in positive numbers. Please visualize. Just try to visualize. Here's your XY, right? Here it is. And your Z's doing this. But plug in positive Z's, positive numbers up here. I'm going to get hyperbolas that are parallel to the XY plane. Do you guys see what I'm talking about? They're going to step, but they're going to be traveling along the X axis. This way and back to this way. Do you guys see what I'm talking about? As soon as I put a negative Z, I have to divide by a negative to get that standard form for hyperbolas. It's going to switch it around to be y squared minus x squared. So above the xy plane, I get hyperbolas along the x-axis. But below, since the sign change, I get hyperbolas along the y-axis. You guys see what I'm talking about? That's going to create a really weird shape. I'm going to show you this in just a minute. I can't draw it by hand. So I'll show you how to do it. Yeah, good work. I got it. Finally gave me a computer that works. Sweet. 12 years, finally got a computer that works. I love that. That's how long you get to put in hard work, folks. 12 years. You get a computer. Sweet. It's like tenure. What values would you use here for Z? What do you want to use? Something simple you can divide nicely with this. I would pick up one. So let's use our 1 degree variable equal to positive 1 and negative 1. Use the same value, but you have to put a positive and negative because you're going to see what the hyperbolas are doing. They're going to change. So if I set z equal to 1, I get x squared minus y squared equals 1. We've already talked about it. We go through it pretty quick, right? These are hyperbolas on the z equals 1 plane. So they look just like they're on the xy plane, but shifted up one whole plane to z equals 1. So at z equals 1, we get hyperbola. Along, those of you who know quantum sections very well, hyperbola is along what direction? X or Y? But if we plug in negative 1, in order to get that standard form, you have to divide by a negative. If I do that, this sign changes, that sign changes. We get 1 squared minus x squared equals 1. So at z equals negative, and down here, my hyperbolas change. Now I have hyperbolas, but they're along the y-axis.
Mm-hmm.
This is the last chance that we get to do this for a while, to draw one of these shapes, so I really want to make sure it sinks in. I know it's been a little while since we did this. I think these are really, for goodness sakes, if you remember this. Whatever variable you're plugging a number in for, it creates a trace at that plane. So if I plug in z equals 1, what's going to happen? I'm going to get hyperbolas. What it's going to happen at z equals 1. Let's pretend that z equals 1. Do you remember talking about this from last time? From last time, we go, okay, wherever you're plugging in, redraw whatever other axes you're not plugging numbers in for. So I would redraw parallels of the x. And y. And at z equals negative 1. I'm going to redraw parallels of the x and the y. And you can see what I'm trying to create. There's the idea of those traces. Remember the traces? You go, hey, you're plugging numbers in, right? Where those numbers you're plugging in, those are along an axis. At that axis, you're going to create a trace on the plane that's level to the border point. So in our case, we have this at really level to x and y, but just shift it at z equals 1. Right there, when we redraw the x and the y, we can draw hyperbola, this hyperbola at z equals 1. And you already told me, but tell me again, what axis are these hyperbolas opening along, the x or the y? It's always the first variable. Which one is it? So this goes something like this. Hyperbolas coming out like that. But down here at z equals negative 1, those hyperbolas switch now. They're the same looking stuff, but now they're going along what axis can I put with what axis? So they're going to be going this way. I know that doesn't look so pretty. Some of it, can you sleep with your eyes open? Goodness gracious. Am I going to help on that? I am, apparently. Goodness. I think it was boring. I could make it worse. I really could. I think of it. Somehow we have to connect this. We got to connect this thing. So these hyperbolas are like going this way and this way. And how in the world does that look? Adjust this here real quick. That's not going to be the best, but it's the best I can do. So, can you see that picture okay for you guys? This right here is a hyperbolic graphboard. I'm going to show you a few things about it. Firstly, it's kind of weird shape. We call it saddle. So it's saddle graph because it looks like a green saddle. Okay, so it's not a saddle graph. But check this out. I want you to see some cool stuff about it. If I do what are called contours, these are level curves. Oh my goodness, what shapes are those? Notice how above the xy plane up here in this region, they are traveling along the x-axis. And below the xy plane, they're traveling along the the y-axis. You can see what I'm talking about. That's pretty cool. Right now, I'm going to say a couple things about this. This is called a contour plot. We get a lot of contour plots in this class. What a contour plot does is it looks from above and creates like a topograph. Have you ever heard of a topographical graph? It says, hey, here's your levels, and it just puts them on a map, like flat. That's what this is doing. All these things are traces of hyperbolas that are surfaced together, and you get this really cool looking graph out of it. You guys understand the idea of a hyperbolic parabola?
Yes.
As soon as you start changing numbers up here, like put in 4 last square, it's going to start changing the nature, the flux of that saddle. If you want to see the last graph that last shape of graph, that's this one. This right here is a basic parabola. That's all it is. It's a parabola. It's basically green. You want to see the contours of it. Those are those ellipses that we just drew. You guys see what I'm talking about? Pretty good. And from the side, they would take parabolas to match this up. To go along the edges of those ellipses, it says parabola. That's why you call it parabola and a hyperbolic parabola. Does this make any sense to you? Do you guys like seeing those pictures like that? Can you visualize it a little better now? That's what they're doing. Obviously, I can't draw them like that, man. I mean, really, mine's just as good when you think about it. So, no big deal. But that shape that we just saw, that's really what this one is. You saw the contours, you saw the really why it is the way it is. So, as if you did. So, I give you a solver, or I give you a surface. Can you right now identify the main things about it? Firstly, what shape it is. Secondly, what axis it's traveling along. And thirdly, can you give me at least 3 traces? Yes or no? Okay, we're going to pause right there.
All right. Just finished 10.6. I'm gonna go over and highlight it. So I kind of can read it over once and then kind of go from there. Alright. So I just finished the cylinders and quadratic equations lecture, but this first part of like a 2-part lecture is basically just going over like the shape and how to draw it basically. The second one goes more into the equations and solving them, I assume. I haven't watched it yet. And then the next one is vectors, and then the next one is vertex. So I'm going to use blue as kind of like a topic, pink as like important, and yellow is just basic information that I should probably know. Cylinders equations only have 2 variables. These equations give a trace of the curve. The curve is directed along the axis of the missing variable. The curve / trace does not change along the direction axis. So if it's 2 variables, so z equals 4 minus x squared, then it's a cylinder. Trace on the x plane, direction on y axis because the axis is missing. Then to solve for it, c minus x squared is a parabola. It's going up 4 on the z-axis and opening towards negative z-axis. So it's on the xz plane. Okay. And surface is intro. Have all three variables. Traces occur on coordinate planes and or on planes that are parallel to coordinate planes. Still directed along the axis, but trace changes along the axis. Determine the surface. Determine the direction axis. Find the trace of the coordinate plane. And find at least two traces along the direction axis. So the first one is the ellipsoid. How you can tell is always to write it in standard form. Which is x squared over a squared plus y squared over b squared plus c squared over c squared equals 1. So an ellipsoid has all positive, all have the power of 2's, and has a constant. The one-sheet paraboloid has one negative, but all of them are still square and is equal to 1, which is the constant. In order to find the intercept, you have to set the negative variable to 0 and set it equal to the denominator, the square root of the denominator, in order to get the three traces. So it's 0 plus minus square root denominator, and it either gets you ellipses or circles. That's good to go. And two-sheet hyperboloid. Also, Lee, thanks for tagging me in your story. Okay. On to the next. So two-sheet hyperboloids have two negatives, but all of them have the power of 2, and all of them have a constant. So they're always directed along the positive axis this time because it's always the odd man out. So it's going to be z squared. And when you set the negative variables to 0 to get the axis intercepts, and then in order for you to get the last intercept, you just choose a number that's divisible by the denominator of the positive variable. Cool. And then I'm so bad at drawing graphs, but I drew a graph. Then cones. I don't usually, so these are my notes, and I don't usually make them pretty just because of the fact that like I'm in 8-week courses and I have to like speed through them, but I think it was a good idea for at least like this section to make it pretty just because of the fact that like there's a lot of information and I don't want to get the information jumbled up with like other graphs since they're so similar to each other. So that's my thought process of note taking. But now moving on to cones, all of them are squared, but one negative and has no constant. So that means it's always directed along the negative axis because that's the odd man out. So setting the negative equal to 0 does nothing because two positives with numbers can't equal 0 unless they're both 0, 0, and that means you don't technically get a shape. So instead of doing that, you just plug in the values for the negative that is divisible by the denominator. So it's either a circle or an ellipse. So basically, if you have a denominator of 36, the square root of that is 6, and that would be plus or minus your, plus minus, that's where your traces would be. So you may either make a circle or an ellipse, and then you just connect those dots together, which is very easy. I should highlight no constant, because this is the start of no constant. Alright, and last but not least, paraboloids and hyperbolic paraboloids. Oh, I used no color. That's okay. So hyperbolic paraboloids and paraboloids are similar in the fact that one variable is not squared, but they still have 3 variables. The difference is paraboloids have 2 squares, positive squares, and the hyperbolic paraboloid has 1 negative square but 1 positive square. So for paraboloids, they open along the axis of the variable with the degree 1. So if it's positive, towards the positive axis, negative towards the negative axis. And then you set the degree of the one variable equal to 0 to get a trace on the quadrant plane. Only works if it's shifted. If it's not shifted, then again find something that they're all going to be in common to divide by in order for you to get a constant, which is 1. And hyperbolic, very easy. Plug in positive and negative numbers 2 degree variable. And then basically the graph looks like a saddle. And that's it. Now, moving on to my next lecture. Wait, look at my pencil case. It's a pencil. Hence the pencil case. Cylindrical and spherical coordinates. So I should turn on my lights. Give me a sec. Oops. It's a little better. Hold on, let me wake up Alvin because he's supposed to be. I'm back.
All right, so our next section, our last section of this chapter, and honestly probably the easiest one, is we're going to start working on cylindrical and spherical coordinates. And the reason why we do is twofold. A lot of times when we're dealing with specific shapes like cylinders, and spheres, we can redefine these rectangular coordinate systems, x, y, and z's, in terms of other coordinates that make our equations way easier and way nicer. Like, well, okay, what's the big deal? I'm used to x's, y's, and z's. That's right, you are. And so when we go to graph them, typically we do x's, y's, and z's because we're not used to these other ones. The more we get used to these, the more other shapes become easier. Furthermore, when you get to the actual integrals, you are used to integrating across a straight line, the x-axis. We are going to start integrating across regions that have areas. And the easier we can define those regions, the easier our integrals become. And we're going to be using cylindrical and spherical coordinates to do that. So in chapter 14, like 3 chapters from now, when we actually get there, we're going to be relying on your knowledge from right here. We do it now so that some of the other stuff becomes easier. We don't have to graph in the next chapter, and one after that, and one after that. But when we finally get to like double integrals, triple integrals, this is going to save a life. It's going to make really hard integrals easier, at least easier. I'm not going to say easy, but at least easier. You guys understand the idea behind doing it? That's the idea. Now, how it works, we're going to start with cylindrical coordinates, and we're going to take off with spherical. Cylindrical coordinates, they literally are just like polar coordinates. Do you remember polar coordinates?
Oh,
Section 10.3, I think, from Calculus 2. Polar coordinates. 10.4. One of those two ones. Polar coordinates, they're not the same thing as rectangular x, y. What they do is they say, I want to give you an angle to the x-axis or the polar axis, and then shoot you off. It was like that, a radius. That's what they did. It was on the x, y plane. Do you remember that? It was a projection of the x, y plane. This is just like polar on the, please listen carefully, I don't want to lose you. Cylindrical deals with r and theta, and it's still on the xy plane. That's this one. It's just that we have to add a z component. So what's going to happen is we're going to have this polar representation of xy plane and say, hey, right where that is on the polar coordinate system, wherever that is, we're just going to take that and raise it up along the z-axis. That's how cylindrical works. It is polar with a z component. Let me show you. So here's polar.
oh wait, I know this.
Polar's on a plane. Polar is on, typically we think of the XY plane, it's just a projection on that XY plane. Polar had R representing the radius to whatever, away from the origin we have, and theta is the positive angle from, or negative angle, but it's the angle from the polar axis. We think of the x-axis. It's still the x-axis. But we want to change the cylindrical. It's even the same order. We still have R, we still have theta, but now we have something that gives us this 3D coordinate system that's not the XYZ coordinate system. It's R, theta, and Z. What's even better, what's even nice, even more better, what's even more better about this is that all the stuff that allows you to translate from rectangular to polar, since the Z is the only new thing, it still works exactly the same. The Z just says, hey, you're on the polar, you're lifted up on the Z, or you're pushed down on the Z. So all the stuff we use to translate between rectangular and polar is exactly the stuff we use to translate between rectangular and cylindrical. And you're gonna like it, because the Z coordinate just doesn't change. Z is Z, and U is U. So the same identities hold true, same stuff for both of these. Now, if you don't remember them, you can always think back to some trigonometry and do some right triangle trigonometry to get these. But x was always represented as r, remember x cosine, that's right. Y, come on.
Or sin theta.
So check it out. Here's what I'm talking about. In 3D, in the R3 coordinate system, we have x's, we got y's, we got z's. We've got a way to translate x's, it's r cosine theta. We've got a way to translate y's, it's r sine theta.
Tan.
Do we need to translate z's? No. The z is the z. The height is still.
Oh.
That's what I'm talking about. The polar changiness is the cylindrical changiness. Z is what? Z equals Z. It's still giving you the height above the XY
I will
plane.
be right back. All right. Ambient. Oh wow. That streamed for almost like 3 hours.
This z is giving you the height above the xy plane, same z, and not even on the same z. That's pretty cool. It's pretty easy to do. We use these identities to go from cylindrical to rectangular. Like cylindrical, you get rectangular. So this is used for cylindrical to rectangular. If we need to go back from rectangular to cylindrical, we use the second set. This is just Pythagorean identity, right triangle trigonometry. Do you remember how much r squared is if r is the radius, the hypotenuse, if you will? How much would it be?
X squared plus y squared.
R would be the square root. The r squared would be x squared plus y squared. Also, a couple other things. Tangent theta, we always define this as well, sine or cosine, but if sine is the y and the x is and then a, how much is z? Z is z, because there's no change there. This is how you would go from rectangular to polar. Oh, sorry, cylindrical. Same thing. A couple notes. We got a couple examples. Literally, the only few things I want you to do is this: be able to translate back and forth from rectangular to cylindrical, from rectangular to spherical. We haven't got there yet. From cylindrical to spherical, from spherical to cylindrical, and then be able to change some equations from rectangular equations into like. R is the distance from the origin to the projection of the point on the xy plane. R is polar, which means R can't travel outside of the xy plane. R is in that plane, which means that R can only go from origin to somewhere on that plane. The only thing we can do on that plane is project the point on that plane. That's what R gives us. So R is not the distance from the origin to the point, it's the distance from the origin to the projection of the point on the xy plane. It's kind of a big deal. The reason why it's a big deal is because when we get to spherical, we have something that is the distance from the origin directly to the point. That's a different type of coordinate system. It's called spherical. One more thing, and this is a big deal. We're about ready to translate between like rectangular and cylindrical, and cylindrical and rectangular. You got to make sure that your quadrants and your octants match up. So a lot of times we can get these two different, especially when we're going from rectangular to cylindrical, we get two different things. We'll say, hey, you're rectangular, you get this tangent of 2 pi or tangent of 2 pi over 3. What is that? Well, you got that one, but if I say tangent inverse of -1, there's a few values that you can get out of that. Does that make sense? For that reason, you got to make sure that when you're changing your coordinate systems, that you're matching up your quadrants and your octants. So I'm going to put that down here. You'll see exactly what I mean in a couple of examples, but match your quadrants and octants when you're converting points.
Hi.
I'd like to show you a picture of how cylindrical actually works, and then we'll start with some examples.
Your scenting is so strong.
What do you mean?
One from Bath and Body Works. Like it's overpowering mine.
Dude, unplug it and put it in the bathroom. Unplug it and put it in the bathroom.
So here's how this stuff works. If we have this point floating out here in space, this point floating out here somewhere in space, you guys see where I'm trying to represent that point? It's like it's floating out here. Look, well, okay, I'm gonna ask you two questions. Firstly, what octave is that point in? Can you visualize it? It's an octave 1. The projection is in quadrant 1. You guys see the quadrant 1? Quadrant 1, quadrant 2, quadrant 3, quadrant 4, the XY plane. You guys see what I'm talking about? Here's what cylindrical does. Instead of going, oh, here's X and here's Y, and you're going to meet it's X, Y, and Z. This is still the Z, but polar takes over for that plane. So polar says from the positive x-axis, you get me? There's an angle from the positive x-axis from origin to the projection of that point. That angle is theta. That is what that is.
Hold up.
Here's a big one that people get kind of messed up on. The arm.
Okay, I think I'm gonna stop the live stream. Thanks for joining me.